Okay, this video is to support your reading of section 8.6. Okay, and this is really cool. I'm pretty fond of this material. This is, again, it's a very mechanical view of cell membranes. Okay, and so we talked in the previous video, previous reading about the form of my cells. Now we're going to talk about what the lipid bilayers that create the cells of the membranes of all cells, what amazing properties they have. Okay, and so the goal of this is to think we're gonna focus on the bending energy. How much energy does it take to bend the cell membrane? And as we do, we're going to see it's quite strong. Now, some things we won't look at mathematically, but that we can draw from, is that the cell membrane is crazy robust. Okay, it does not like to be poked. It is pretty strong, and it can do so without any energy source, any like ATP, and so it can form. These things can form spontaneously through just the hydrophobic effect, which is an electrostatic, a chemical force, but also with origins with entropic forces, and so they can form spontaneously, and they're crazy robust, which just tells us that they've been really built up, really designed, evolved, however you want to say it, to really be perfect for the needs of molecular life. We'll find that some of the properties are just right for energy transport or material transport through the membrane, and that different proteins, different molecules have been able to be designed to fit just right within it. So nature's done a great job of doing this. Okay, so one thing that we're going to consider is that they are very fluid in the membrane. So molecule can move around the membrane. So like if I were a molecule right here, I can move this way and this way with really no thermal energy. Is totally sufficient for me to move this way and this way. But if I try to come in or out, or I try to pull the membrane in or out, that takes a lot of energy. That's where the robustness of the membrane comes from. So that's what we're going to focus on in this section. Really cool stuff. Okay, so consider a lipid membrane. We could call it a top layer and a bottom layer. All right, and as in that picture we showed in the previous video, you can go back to that, look at that. But it's the tails are protecting each other by the heads. Or the tails are protected by the heads in a sandwich form from the watery environment around. So our question is, well, what would it take to bend this thing? How much would it take to bend this thing? So if you think about it, if we choose kind of the middle of it as a midplane, well, that means we have to shrink the bottom layer and we have to grow the top layer. So a negative delta A and a plus delta A. All right, so if we try and consider the change in free energy to do so, we look at the top layer, and any function, this is something to note if you haven't seen this before, any function can be written as a series of a power. Okay? So we want to know how this energy depends on the change in this area. Now if we choose it, we look at a single molecule, just a single molecule, then this area is really small, and so when things are small, you can expand it in a series function. So any function can be expanded in this series of powers. You have constants plus coefficients times the linear term plus coefficients times square term plus so on and so forth. Okay. Now what we're going to see is with the for the top layer, the constant value is going to switch places because whatever its natural state is to start with, it's going to be in some manner for the top, and it's going to be opposite for the bottom. So these constants would cancel out. They don't really affect much anyway. Okay. Now the linear term, in fact, all odd terms, so the linear term, the cubic term, fifth term, okay, fifth power term, because we're decreasing the bottom by the same amount as we increase the top, then these are going to cancel out. Okay. And then this one, the squared term, or the quadrat, or the to the fourth power term, they will add. Okay, but we're going to assume that delta is so small that third, fourth, higher powers are going to be crazy small, because by raising something small to a power makes it extra small. So we'll just forget those terms. So this will be an approximation, assuming delta A is small enough. Now, if we consider delta A to be the size of a molecule, that's pretty darn small, so we're good. So the total change of free energy necessary to do this will be the sum of the two, and we end up with just twice that second term, the quadratic term. So we can make a definition then, noting that this is for two molecules, one on top, one on the bottom. So if we look at what is the free energy per molecule, we just divide this by 2, and then we're just going to call this constant 1/2 K. Now later we're going to call it a different constant, so it really doesn't matter. But the reason why we choose this is because it looks very much like Hooke's law, which it ought to, because this is an elastic effect. We even talked about bending of areas and called that a surface tension. And that has very much the same idea as a spring constant. Only we need to note carefully that the spring constant is the same in idea only. It is not the K that would be found in Hooke's law, because we can see it doesn't have the right units. Okay, in order for this side to equal this side, this is an energy. Molecules don't have units, and so area squared is meters to the fourth, and so energy is newtons times meters, and so this ends up being a newtons over meters cubed, which is just not the same thing as in newtons per meter like it would have been for Hooke's law. Now, for our case, we just really care about energy, so we'll just leave it as the joules over meters to the fourth. Okay, so the whole point of this is not that we're going to use it, it's just remember that's not the same K as in Hooke's law, but it's the same idea of the K in Hooke's law. So this is now our free energy change when you change the area. Okay, let's see what this does for us. Let's start by thinking about what if I'm going to try and wrap this bilayer around a sphere. Okay, we'll focus on just one of the molecules right now, just one of the molecules. We'll go back to the whole bilayer in a second. Okay, but let's just pretend we're wrapping one set of molecules around a sphere. Now I want to point out the text does a cylinder, which is a little different. It's a quasi two-dimensional surface where this is a true three-dimensional. But the process is going to be the same, in fact a little bit easier for the cylinder, but I just want to point out, so after watching this, you can go back and maybe look at the reading and do the cylinder and try and follow these steps to clarify what the author does. So our idea is we're going to wrap this bilayer around a sphere, which means the part that's closer to the sphere, we're going to call that A, and it's at a radius r away. And the part away has to get stretched somehow. That's A plus delta A, and it's at a distance r plus d with the length of this molecule we'll call d. Okay, so what we need to do is figure out what delta A is, and let's do it by looking at what A is itself. So A would be, there are n molecules covering the surface, then it's just the area of the sphere divided by n. Well, same idea for a bigger radius, A plus dA, so the total area up here ought to be equal to the area of a sphere of that radius divided by n. Okay, if we factor out an r, in fact an r squared, pull out an r squared, okay, like that, we would be left with the 1 plus d over r quantity squared. So again, check that, make sure it's clear. If I multiply this r squared through, distribute it through, it would come in, it'd be a single term here, okay, and then it would cancel out this term here, so we get r plus d as we had. Now obviously the reason for that is all that stuff right there looks like A. So I just write it as A, and I get 1 plus d over r quantity squared. But this is something cool. D is the size of the molecule, r is the size of the sphere, which is like the size of a cell. 10 microns versus a nanometer or 2. Well, this term is crazy small, and so what it allows us to do is do some more series expansions. Okay, I can expand this term, and you don't have to have this memorized, but this one is pretty common, so it's not bad to memorize it. Okay, but when you have 1 plus, here, I'm going to write that down actually. If you have let me use a different color to emphasize, this is an example. 1 plus some small number to a power. Okay? to the first two terms, that is, I should do approximately equal. That is approximately equal to 1 plus the power, come on, times that small number. There are other terms in the series expansion, but we can ignore them. Okay? So that is a series expansion. That's something good to memorize. That happens a lot in physics. But in doing so, we just pull the power of 2 down in front of this small number, this d over r. Okay? Then we can distribute that a through again. And then we can see a plus delta a equals a plus 2ad over r, which tells us delta a is 2ad over r. So we found delta a, which is what we needed, so now we can find our delta f. Okay, so remember that was for, we did that to find that delta a for a one piece of the bilayer. So we're just going to multiply by 2, because that was for a single molecule is this thing. So we just multiply by 2, and now we can plug this delta a into here. Okay, so here they are again. I just rewrote that down. In fact, I took a picture of the screen and copied it. It was really cool. So I'm going to take this, plug it in, and so we'll have our free energy for the 2 molecules is going to be equal to this quantity here. Note all this stuff is squared. I squared all of that. Now I'm going to factor it a little bit weird. Okay, that's simply because we have a new constant that's going to be commonly used. So I factor out, this is squared, so I have 2 factors of 2, factor 1 out, have that k, keep the d squared, and I leave 1 factor of a here and another one here. So that still is a squared, as this is 2 squared, which is 4. That's all the numerator, and then I have r squared down below. Well, all this stuff here, okay, all that here is a property of the material. Okay, this elastic nature of it, the size of the molecule, and the area of a molecule. And we can call that all kappa. Okay, so kappa is this value we use. So if we divide by this area, then we have the free energy change per unit area, and it's simply equal to twice this kappa value divided by r squared. Okay. Now for molecules commonly used in synthetic lipid bilayers, and they're not too far different than real biological lipid bilayers, kappa has it's an energy value. Notice this is area, r squared has units of meters squared, this is energy, this must have units of energy. The kappa value generally is on the order of about 15 or so, 10 to 20-ish kBT. So that kind of gives a good energy scale. All right. So I want to reemphasize, this is the energy per unit area for a spherical surface of radius r. This is how much energy per unit area you'd have to do to create a spherical surface. All right. And so notice that it takes a lot of energy to make a small radius, or that's called a big curvature, or a tight turn. If you want to make a tight turn, bend the membrane a little bit, bend the membrane really sharply. Okay, very tight turn. That takes a lot of energy per unit area. But you know what's interesting is we can show here that the energy it takes to make a sphere, a complete sphere, is independent of the radius. Let's see how. So if we want to see what is the energy it takes to make the whole sphere, bend the thing into a whole sphere, well, that would be the energy per unit area times the area of the sphere. Well, the area of the sphere is 4 pi r squared. And so it's 2k over r squared. We end up with 8 pi k. It's independent of the size. So that might seem, what? You just said it takes a lot of energy to make a tight turn, but then you just said that it doesn't matter how big of a sphere you make, it uses the same amount of energy. Well, what you have to think about is the energy per volume. How much energy do you need to have ready in a location to do it? Okay, so to make a small sphere, I say it's pretty hard, okay, rather than making a big sphere. So if it's the same energy, no matter how big the sphere, well, what's the energy per volume? The energy for the space, localized space. So if we divide it by the volume of the sphere, we get back a constant over r cubed. And so it does take a heck of a lot of energy to create a small sphere than it does a big sphere in terms of localization. The actual energy in the sphere isn't as important, but you have to get that energy to a smaller location versus having it spread out. So if you think about a cell's huge, and there's lots of machinery to create ATP. Well, that means you've got lots of ATP available to make that 8 pi kappa. You got lots of ATP to be able to make this. But if you're making a really small nobule, a really small vesicle or something, you got to get that same amount of energy to a smaller spot, and that's a lot harder. So it is still pretty hard. Okay, so we can now wrap this up with some good concrete examples, and this can help us understand the rigidity of the cell and its robustness. So let's, for example, take a look. Why are cells smooth, or are they kind of got waves all throughout them? Are they bumpy, or is it a pretty smooth surface? And we're going to find that they're pretty smooth. It takes a lot of energy, as we just saw. It takes a lot of energy to make a small bump. Okay, all right, or a lot of localized energy. So let's just make an example. Let's suppose the cell surface is made up of all this waffling effect. And there's just all these turns that are of radius r. We'll have a section that we'll call an area A. All right? How much would it cost to make this structure? All right, so we go back. Here's the energy it would take to take it from straight to bent. Well, that's how much per unit area times the area. So we plug it in here, and we find what radius would we have in terms of that energy available, okay, and the area we're working with. Okay, so we got a lot of unknowns here. So let's go ahead and think. Well, let's suppose it takes about 20 ATP. Okay, sorry, it takes n ATP. I apologize. 1 ATP. If you look up in the appendix, 1 ATP has the energy of about 20 kBT, 20 times the thermal energy. And remember, kappa is 15. Okay, so we can get rid of our energies here. And so by plugging all our numbers in, we can see that the radius, in terms of how many ATP we'd need, okay, in terms of n ATP, is just 3 over 2n times the area. So let's just get an estimate here. Let's suppose we need 20 ATP. All right, how big of an area would I need to be able to make this 20 ATP? And let's choose a cell. Okay, let's take a cell radius size. Now remember that we're going to take the area to be the cell size, but we don't know what this curvature is. This curvature we're seeing, can it be tight, or does it have to be big? So if we plug in a cell, if you do 4 pi r squared for a 10 micron radius cell, you're going to get about 1,000 microns squared. Okay, so plugging these two numbers in, we get a radius of 8.7 microns. Well, that's about the radius of a cell. So that's saying that the cost of doing this means that those curvatures need to be not very small. They have to be about the size of the cell. Okay, and 20 ATP are plenty available for that size. Okay, now I do want to clarify that that bilayers. This does tell us that bilayers are generally very rigid locally, so they don't have a lot of little bumps. But globally, they're pretty flexible. It's pretty easy to get 20 ATP for a whole cell to do things. But you can also have machinery at some localized spots, maybe some right here, maybe some right here. You have machinery to create enough energy, ATP, to be able to push and bend something close by. Okay, and something that's really cool about that, I think I had no. Well, let me finish this and I'll go back to it. Okay, and so you can do it. So what I want to emphasize is you can make tight turns, but it takes a lot more energy localized at that spot. Okay, so generally cells are fairly rigid locally, but have global flexibility unless you have machinery to bring energy to that localized spot. Let's go ahead and see, as a different way of thinking about it, what if the energy you have is not n molecules of ATP, but the thermal energy available? What kind of curvature could you get with just thermal energy? Okay, so same idea, only now we just have kBT. So that gives A, or R equals the square root of 30 times the area. So let's choose a small patch because that's going to be what's affected mostly by thermal energy. So like a 10 by 10 nanometer patch. Okay, if you plug that in, you get about a 50 nanometer radius. Now that's pretty flat. You know, a 10 by 10 patch with 50 nanometer radius, if you think about it, that's a pretty flat object. All right? The ratio of the area and the radius are pretty small. And so it again is telling us that locally the membrane is pretty rigid. Okay, I wanted to come back here and just sum up one thing that's really cool, and something you really should look online about. But there's something called clathrin-mediated endocytosis, and basically this is a molecule, a set of proteins in a whole signaling pathway that helps to form these buds. Because it's so hard to create small buds off of the membrane, there's actually active processes that come and grab it and create a cage that sucks that cell in, and even other proteins that go to pinch it off. It's a really cool process. So I'm just kind of giving you a teaser here, but the important thing is that because of the energy involved with these tight curvatures, there needs to be active processes, and clathrin-mediated endocytosis is one example.